In the early 1950s, at the height of the Cold War, the U.S. Navy recognized the growing threat posed by Soviet submarines. To counter this, they developed a top-secret undersea surveillance network known as SOSUS, Sound Surveillance System. SOSUS began under Project Jezebel, funded by the Office of Naval Research, ONR, and built in partnership with AT&T and Western Electric. The system consisted of hydrophone arrays placed on the ocean floor, connected by undersea cables to shore-based processing stations called NavFacs, dosits.org. The first array, 40 hydrophones stretching about 1,000 feet, was installed at Eleuthera in the Bahamas in January 1952. After successfully detecting a U.S. test submarine, the Navy expanded the system along the U.S. East Coast. SOSUS used the SOFAR channel, a deep ocean sound channel that allows low-frequency sound to travel thousands of miles, to detect submarines at great distances, dosits.org. The acoustic data was sent to NavFacs, where it was processed with the Low-Frequency Analysis and Recording System, or LOFAR. LOFAR grams displayed sound frequencies over time, allowing operators to recognize the unique acoustic fingerprints of different submarine classes. The system proved highly effective in tracking both noisy diesel subs and quieter nuclear subs. As the Soviet submarine fleet grew, the SOSUS network expanded internationally, including stations in Iceland and Wales. By the mid-1970s, it consisted of about 20 NavFacs, 2 ocean processing centers, and roughly 3,500 personnel. In the 1980s, SOSUS technology improved with longer undersea cables, and the shore stations were gradually replaced by naval ocean processing facilities, NOPFs, such as the one in Dam Neck, Virginia. The fixed arrays were supplemented with SURTAS ships, creating the integrated undersea surveillance system. By the late 1980s, IUSS had 11 NavFac NOPF sites, 14 SURTAS ships, and around 4,000 personnel. However, towards the end of the Cold War, Soviet intelligence, through the Walker-Whitworth spy ring, learned of SOSUS, prompting them to build much quieter submarines. This significantly reduced IUSS detection capability. By around 2010, the system had been scaled down to just a few NOPFs, a small number of SURTAS ships, and about 1,000 active personnel. From the start, SOSUS also contributed to science. Early experiments tracked ocean currents using SOFAR floats. Later, the system was open to researchers studying underwater earthquakes, seafloor volcanoes, whale migration, and even climate change, by monitoring ocean temperature through sound transmission times. The Sound Surveillance System, SOSUS, was a Cold War-era passive undersea surveillance network developed by the U.S. Navy to detect Soviet submarines. To protect its secrecy, it operated under the cover name Project Caesar, and its shore-based facilities were called NavFacs, supposedly for oceanographic research. SOSUS took advantage of the SOFAR channel, a natural deep ocean sound channel that allows low-frequency sound waves to travel thousands of miles with little loss of energy. Arrays of hydrophones were placed on the ocean floor along continental slopes and seamounts, connected to shore stations by undersea cables. These arrays could detect incredibly faint signals, sometimes less than 1 watt, from hundreds of miles away. By combining data from multiple arrays, operators could pinpoint the location of a submarine through beamforming and triangulation. Development began around 1949, with the first test array installed at Eleuthera in the Bahamas in 1951. A full operational 40 hydrophone array followed in 1952. Over the next decades, SOSUS expanded into a global network covering key choke points in both the Atlantic and Pacific Oceans. The system gave the United States an unprecedented ability to monitor enemy naval movements on a worldwide scale. In the 1980s, SOSUS was integrated with mobile towed array systems like SURTAS, forming the Integrated Undersea Surveillance System, IUSS. The true purpose of SOSUS remained classified until 1991, when its mission was declassified, and personnel were finally allowed to display their service insignia publicly. After the Cold War, many of the original NAVFAC stations were closed, and processing was consolidated into Naval Ocean Processing Facilities, NOPLs. While its military role decreased, parts of the system were repurposed for civilian science, including monitoring earthquakes, volcanic activity, and marine life over vast ocean areas. At the end of World War II, the United States recognized the rising threat posed by advanced Soviet submarines. In response, the U.S. Navy began developing a groundbreaking undersea surveillance system known as SOSUS, initially under the code name Project Jezebel, later referred to as Project Caesar to conceal its military purpose. SOSUS took advantage of the SOFAR channel, a natural deep ocean sound wave guide that allows low-frequency sounds to travel great distances. Arrays of hydrophones were laid along continental slopes and connected via underwater cables to onshore processing centers called NAVFACs. When sound data reached NAVFACs, operators analyzed the acoustic signals using LOFAR grams, which display frequency over time and reveal unique acoustic fingerprints of different submarines. The first full-scale array, a 1,000-foot-long line with 40 hydrophones, was deployed near Eleuthera in the Bahamas in early 1952. Tests confirmed it could detect a U.S. test submarine, spurring expansion along the U.S. eastern seaboard and eventually across both oceans. By the mid-1970s, SOSUS had grown into a global network with around 20 NAVFACs, 2 ocean systems commands, and some 3,500 personnel stationed worldwide. In the 1980s, technology advanced. The system incorporated Naval Ocean Processing Facilities, NOPFs, and integrated mobile assets like SURTAS ships, forming the Integrated Undersea Surveillance System, IUSS. At its peak, IUSS included 11 fixed sites, 14 SURTAS vessels, 2 commands, and roughly 4,000 personnel. Eventually, the Soviets learned of SOSUS via espionage, leading them to develop quieter submarines that reduced the system's effectiveness. By 2010, the infrastructure had scaled back to just a few NOPFs, a handful of ships, and about 1,000 personnel. Even during its military heyday, SOSUS contributed to science, tracking ocean currents with SOFAR floats, studying underwater earthquakes and volcanoes, monitoring whale calls, and even measuring ocean temperatures for climate research. The Sound Surveillance System, SOSUS, was a top-secret Cold War-era undersea surveillance network developed by the U.S. Navy, designed to detect Soviet submarines using passive sonar arrays placed on the ocean floor. Due to its classified nature, the program operated under the code name Project Caesar, with shore-based processing centers referred to simply as naval facilities, NAVFACs, covering the system's actual purpose under the guise of oceanographic research. In 1985, SOSUS evolved into the Integrated Undersea Surveillance System, IUSS, incorporating not only fixed ocean floor arrays, but also mobile platforms such as the Surveillance Towed Array Sensor System, SURTASS. Despite the expansion, all system activities remained under the pretense of oceanographic operations until 1991, when the mission was officially declassified and the real purpose was acknowledged publicly. The Sound Surveillance System, SOSUS, was a classified, passive underwater surveillance network deployed by the U.S. Navy during the Cold War to detect Soviet submarines. To mask its true mission, it operated under the cover name Project Caesar, and shore stations were labeled merely as Naval Facilities NAVFACS, purportedly for oceanographic research. SOSUS leveraged the SOFAR channel, a natural deep ocean acoustic waveguide that allows low-frequency sound to travel vast distances with minimal attenuation. Arrays of hydrophones were placed on continental slopes and seamounts, connected via undersea cables to NAVFACS on shore. This setup enabled the detection of faint acoustic signals, sometimes less than 1 watt, over distances of hundreds of miles. Using beamforming and triangulation across multiple arrays, the system could estimate a submarine's position, origins of SOSUS trace, back to 1949, following a study group formed by the U.S. Navy's Committee for Undersea Warfare. By 1951, the first experimental 6-element hydrophone array was installed near Eleuthera, Bahamas, with a full-scale 1,000-foot, 40 hydrophone array deployed in 1952. Growth continued with NAVFACS established from Nova Scotia to Barbados, with further installations in the Pacific during the mid to late 1950s. In 1985, the system evolved into the Integrated Undersea Surveillance System, IUSS, combining fixed arrays with mobile platforms like SURTAS, Surveillance Towed Array Sensor System. Its mission remained classified until 1991, when it was declassified and personnel were allowed to wear official insignia reflecting their roles. From its inception, the Sound Surveillance System, SOSUS, operated under the strictest secrecy. Classified at the secret level, the program was kept on a strict need-to-know basis, equivalent to sensitive compartmented information, even though its official cover described it as oceanographic research. To conceal its true mission, the system was designated Project Caesar, and its installations were known as NAVFACS, Naval Facilities. Personnel held innocuous titles such as Ocean Technician or Oceanographic Research Watch Officer, and the commands were described as Ocean Systems Atlantic/Pacific, rather than their actual names under SOSUS. This cloak of secrecy extended even to internal communications. The operational data sent to the fleet used cryptic message formats labeled Rainform, hiding both the source and the significance of the intel. As a result, many fleet commanders were unaware of SOSUS's real purpose or performance. By 1985, SOSUS had evolved into the Integrated Undersea Surveillance System, IUSS, incorporating mobile towed sonar ships, SURTASS, but it retained its top-secret status, Turn 0 Search 12. It wasn't until 1991, after the Cold War had ended, that the mission of SOSUS and IUSS was finally declassified. The oceanographic cover was dropped. Personnel could now wear appropriate insignia, and the commands were renamed Undersea Surveillance Atlantic-Pacific. Beneath the vast and silent oceans lies one of the most advanced and least-known military technologies in history, the Integrated Undersea Surveillance System, or IUSS. Originally developed during the Cold War as the SOSUS network, its purpose was to detect and track Soviet submarines using a hidden chain of hydrophone arrays anchored to the ocean floor. The project was highly classified for decades, and its existence wasn't officially acknowledged until the early 1990s. Today, the system remains operational, managed by the Commander, Undersea Surveillance, headquartered at Dam Neck, Virginia Beach. It combines fixed seabed sensors with mobile surveillance platforms, such as towed array ships, capable of detecting objects and vessels thousands of miles away. These arrays provide real-time intelligence to the U.S. Navy and its allies, acting as an underwater early warning system that helps secure vital sea lanes. A notable milestone came in January 2020 when Captain Brian Tadakin took over command from Captain Scott Lewers. Under Luers's leadership, the program expanded its manpower and modernized its technology, introducing the SOSUS expeditionary system. This mobile towed array capability, first deployed in the Atlantic in 2019, extended the network's range and improved detection precision, allowing for more flexible and rapid responses to potential threats. The scope of the operation is vast, with over 1,200 personnel, including military members, civilian experts, and contractors. The IUSS operates around the clock in multiple theaters. Data gathered from its listening posts is shared with allied forces, enabling coordinated anti-submarine operations and reinforcing global maritime security. While its primary mission remains military, the IUSS has also become an important tool for science. Its hydrophones can monitor undersea earthquakes, volcanic activity, and oceanographic conditions. Marine biologists use its data to track whale migrations and study other deep-sea species. This dual-use capability blends national security with environmental research, showing how a system born from wartime necessity can also serve peaceful purposes. From its secretive origins in the tense years of the Cold War to its current role as both a guardian and a scientific observer of the seas, the undersea surveillance network has quietly evolved. Its future will depend on advances in sensor technology, international cooperation, and the ability to adapt to new challenges. But one thing is certain: the oceans are still being listened to, and their secrets are still being heard. Originally built as a top-secret Cold War defense system, the Sound Surveillance System, SOSUS, was designed by the U.S. Navy to detect Soviet submarines. After the Cold War ended, parts of this vast network of underwater hydrophone arrays were declassified and made available to scientists, transforming SOSUS into a powerful resource for ocean research. SOSUS hydrophone arrays have recorded the distinctive low-frequency calls of blue whales and fin whales, sounds often between 10 and 25 hertz that can travel hundreds or even thousands of kilometers underwater. These calls are nearly impossible to track visually, but SOSUS data allows researchers to locate and monitor whale populations across vast distances. Using matched filter techniques, scientists can pinpoint whale calls on multiple arrays, and aircraft patrols have later confirmed the presence of whales in those locations. Beyond marine biology, SOSUS can also detect undersea earthquakes and volcanic eruptions. Seismic events create underwater sound waves, known as T-waves, that travel great distances through the ocean. Hydrophone arrays can capture these signals and allow scientists to determine the exact location and timing of seismic activity on the ocean floor, often faster than traditional seismic networks. Sound travels faster in warmer water, so by measuring the time it takes for low-frequency sound to move between hydrophone arrays, scientists can detect changes in ocean temperature over long distances. This method, known as seismic ocean thermometry, has achieved accuracy down to 0.001 degrees Celsius in studies, helping track global climate change and ocean warming trends.